Welcome back. Today we are talking about Leslie matrices. Now this is an application of matrices that deals with a population, deals with growth rates. We talk specifically about survival rates and birth rates. We're going to start with a simple example just to get us used to using them, and then we'll go into some questions. All right, so firstly, the population is split up into age groups. Okay, so if we got age groups and then the age range. All right, so we're going to do 1, 2, 3. We're going to say there's 3 age groups. The age range for 1 would be 0 to 3 years, and then we would go 3 to 6 years, and then 6 to 9 years. The age group is always split up evenly. And of course, this age range is in years. Okay, so we've got our age group and our age range. Next, we've got to talk about the initial population of the species. And this can be anything. We can use it to describe snakes, spiders, cows, anything we want to do. There's no specific population in this example, but it can be applied to any population. So the initial population, P0, we're going to say is 400 from the 0 to 3 years, 400 from the 3 to 6 years, and 400 from the 6 to 9 years. And that is a matrix, just a column matrix, 3 by 1. 3 by 1 matrix, 3 rows, 1 column. Okay. Next, we set up the Leslie matrix. So this is where the interesting things happen. We're going to use L for Leslie matrix. And the way it's set up is we have B1, B2, and B3. I'll just make that a bit neater. B3 along the top. And then we've got S1, S2, and zeros everywhere else. Now, let me just explain that for a second. The B's stand for birth rates. Okay? So B1 would stand for the birth rate of the age range from 0 to 3 years. Okay, this B1 directly relates to this age group, 1, okay? And it would be the birth rate of this age range. This B2 would be the birth rate for this section of animals or people, and then this birth rate is for this one. Okay, this survival rate here relates to how many of these 0 to 3 old creatures live past that age range. And this survival rate 2 is how many of these live and move on to the next one. Okay, we don't have an S3. Well, that's because that's as old as they get, 6 to 9 years. Let's say maybe this was a fish. Maybe these fish only live to be about 8 years and they don't live past 9. So that's why you don't have an S3 or a survival rate for the last age range of the species. Okay, now that we've set that up, we're going to use some initial values. Okay, we're going to say that our Leslie matrix, we're going to say the birth rate for the young age group is actually going to be 0. We're going to say that from 0 to 3 years, they're still maturing. Okay, the birth rate of the middle age range from 3 to 6 is going to be 2.3, and the birth rate of the old species is going to be 0.4. So by 6 years old, they're generally not having any more children. Okay, so this 2.3 for birth rate 2, that's saying that on average, every one of the population has approximately 2.3 babies or offspring. Okay. Now the survival rate we're going to put in for the youngest age group is 0.6. We've got zeros everywhere else, and the survival rate of the middle age group is going to be 0.3, and then a 0 to finish off with. So this is going to be our finished Leslie matrix for this population. And of course, this is just an example. You could look up birth rates and survival rates for certain animals or species, and of course, it's probably given to you in the question. Okay, now what we're going to do is we can find the sizes of the age groups at the end of the first 3-year time period. Because remember, this age range and age groups, they're split into 3 years. So when we do our first sort of age step, our first 3-year time period, P1, okay, that's going to be equal to L, our Leslie matrix, times P0. All right, so this is a 3 by 3 matrix multiplied by a 3 by 1 matrix. So remember, the Leslie matrix has to go first, and then the population matrix. We can't do it the other way around. We've decided that we can't do that with matrix multiplication. Okay, so our Leslie matrix is 0, 2.3, 0 0.4, 0 0.6, 0, 0, 0, 0 0.3, 0. There's our Leslie matrix. Now our population matrix started off with an even number in all 3 age ranges. And maybe pause the video here and just have a think about what was your prediction? What do you think's going to happen with these populations? Is the population going to have a massive baby boom? We're going to see more creatures in the lower age category, or we're going to see more in the older age category? Are we going to see a massive decline across all 3 age categories? Have a think, and then resume the video when you've maybe tried this multiplication yourself. Okay, so to do this multiplication, of course, row by column, we're going to end up with a 3 by 1 matrix. Okay, that's what we want. We want a population at the end of it. So P1 is going to be equal to 0 times 400 plus 2.3 times 400 plus 0.4 times 400. Right, that's the first row. Then we're going to have 0.6 times 400 and 0 times 400, and then plus 0 times 400, that's just going to be 0. Then the last one, we've got 0 times 400, 0, plus 0.3 times 400. So 0.3 times 400, and then we're going to have 0. We're going to have 0 at the end. Okay. There's our population matrix, and then I can simplify that. 2.3 times 400. Let me just grab my calculator. 2.3 times 400 plus 0.4 times 400 is going to give us 1,080. And then 0.6 times 400 is 240. And 0.3 times 400 is 120. So that is our new population after the first 3-year time period. And of course, we can do this again. We can find P2, and that's going to be equal to our Leslie matrix times P1. Okay, and then our Leslie matrix is the same as before. Just going to copy that. There's our Leslie matrix, and that's going to be times by P1, which is our new population. Copy, paste, there it is there. All right, and that's going to be equal to, well, we do the same thing again. It's going to be, I'll do it underneath, I'll run out of space otherwise. It's going to be equal to 2.3 times 240, because the first one's 0, so it's 0 times that, 0. 2.3 times 240 plus 0.4 times 120. That's our first row. Now you can see what's happening here. So each one of that age group is being multiplied by 2.3. 2.3 times 240. It's something to note, I didn't mention it earlier, but this population is only the female population. Okay, because they're the ones that have babies. They're the ones that reproduce. So for every female in the population in that second age group, we are multiplying them by 2.3 because they have on average 2.3 offspring. So we've got to multiply that age group by 2.3. We're going to get a value. But also the second age group, 120, is going to be multiplied by 0.4. Not all of those... See, it's less than 1, so not all of those females reproduced, but some of them do, is 0.4 from each on average, each of those. So now the next row will have 0.6 times 1080. So only 60% of the 0 to 3 years survive. So it's 0.6 by 1080, and then it's 0 for the rest. And then the last one, we've got 0.3 times 240. So only 30% of that middle age group goes on to live from 6 to 9 years. So let's put our brackets around here, and let's simplify that a little bit. P2 is equal to, so 2.3 times 240 plus 0.4 times 120, 600. 0.6 times 1080 is 648, and then 0.3 times 240 is 72. Alright, so now we have our second population amount, okay? And it's jumped around a bit more, but it's also evened out. So initially we had 400 in each of the categories. Then we had this really big baby boom, but the middle and upper age age groups went down a lot. And then we sort of see this happen again. The babies before, these babies up here, these babies grow old and increased the second age group, okay? But a lot of these did not make it to the last age group. Now it's going to be interesting to see what happens again in our third time interval for the next 3 years, because a lot of this 648 are going to move on to this last age group, approximately 30%. We can do that right now without even doing the matrices. So 30% times 648, that's going to give us 194. So it's going to go up again, but still not back to its initial age, the initial population amount. We can also total these numbers, as of course we're talking about female population. We could total these numbers to find the total female population, and that will just be 600 plus 648 plus 72, which equals 1320. Okay, that's our total population. And you could do this for the initial population, after first time period, and up to 5 time periods if you want to. And then you could graph those population changes over time. You can use Excel for this. So if you want to find the population, say, in time interval 20, that's what we're going to have a look at next. We're going to find, say, the population after k intervals. All right. Looking at our initial scenario, we had P0, all right, and then we had P1 equals L times P0, all right. Now P2 after the second time interval was L times P1, your first population. Your first time interval. But we know that P1 is equal to L times P0. So what we actually have is L times L P0, all right, which is the Leslie matrix squared times P0. For the third time interval, that was L times P2, which is L times, well, P2 we found was this. So that's L squared P0, which is L times L squared, which is L to the power of 3 P0. So just by having the initial population and the Leslie matrix, which is the birth rates and the survival rates, we could work out the population after any time period. So in general, the formula for pk is equal to L to the power of k. See here how this 3 is the same as this 3. It's the same. L to the power of k multiplied by the initial population. Okay? This way we can find the population after any time interval. Okay, so here's some examples, alright? Consider the following Leslie matrix. So L equals 0, 0, birth rate 3. So we're saying the first two birth rates are 0. They don't mature until they're in their third age range. We've got 0.25, 0 and 0, 0, and we have 0.5 and 0. So not many of the young ones survive, but once they get to the middle age range, at least half move on. All right, and we're saying that our initial population, P0, is equal to 1,000. We've got 1,000 babies, 0 and 0, nothing in the older age ranges. So it's possible this is some sort of experiment. They've just brought some babies into captivity and seeing how they're going to raise in captivity. So we're going to investigate the long-term behavior of the population if, so A, B3 equals 8, B, B3 equals 4, and C, B3 equals 10. So we're going to change our birth rates now. We're going to say birth rate 3 is going to be 8. We're going to start with A. Okay, so A, we're going to now, you have to use our calculator here. So if I bring this up, okay, we're going to store these matrices in our calculator. So in run matrix, so we need to now store these matrices in our calculator. So on the home screen and the run matrix, press exit. So we're back on the main options here. We're going to press F3 for matrix. Okay, we're going to store our Leslie matrix as matrix A. So we're going to press enter, and it is a 3 by 3 matrix. Okay, enter. We've got 0, 0. We've got 8. Okay, we've got 0.25, 0 and 0, and then we've got 0.5 for that second survival rate. Then we can press exit. And now matrix B, we're going to do our initial population, and that is 3 rows and 1 column. So initially we have 1,000 and then 0, 0. Press exit again. So matrix A, okay, L equals matrix A, and P0 equals matrix B. Alrighty, so let's just find P1. So P1 equals L P0, which equals what it's going to be. So it's going to be mat A times mat B. I'm going to do that on a calculator. So to get our matrices up, we want to go options, matrices, mat alpha A times matrix alpha B. Press enter. And here is our P1 matrix. So that is equal to 0, 250, and 0. Which makes sense, right? 25% move on to, from the babies, move on to the second age range. But there were no seniors to create new babies. So there's no one in the first age range. Okay? Now let's have a look at P2, which is L to the power of 2, P0, right? Remember that. So that's matrix, well, we can use our brackets. So matrix A squared times matrix B. All right, so here's our our second time jump. That equals 0, 0, and 1, 2, 5, which again makes sense. In our previous matrix, there was no one old enough to have babies, so there's nothing up here. And there was no babies in this column to move to our, in this row to move to our second age range. All we had was middle-aged middle-aged of the population moving into the older range. And 50%, that was the survival rate. So that makes sense. Now what about P3? So P3 is going to be L to the power of 3 P0. Let's go back to our calculator. So we got brackets again, matrix A, and that's going to be cubed now. Cubed times matrix B Oh, that's interesting. We've got 1,000. So that equals 1,000. Why is that interesting? Well, that was our initial population. What happens if you've got a matrix, right? A times B, any matrix A times any matrix B, and you get B. That's weird. Here we had L cubed times P naught equals P naught. Well, that means that therefore L cubed must be the identity matrix, because that's the only way you can get two matrices multiplied together and get one of the matrices back. All right, and let's have a look. If we just do, go back up for a second and delete matrix P, there we have it. So the Leslie matrix cubed is the identity matrix. Okay, so that's the long-term behavior of the population for A. The population will continue to cycle through these population states because L cubed is I. So every 3 years, not 3 years, every 3 age time periods, we're going to get the initial population, and then we're just going to keep cycling through it every 3 time periods. Okay, now what about if we had 4 as our birth rate? Okay, let's go into let's exit out of here. Let's go back to our matrices and matrix A, and let's change now our age range to 4. Enter. Exit. Exit again. Now let's just go back up here, and we can just press enter, and we'll get all of our answers again. So press enter. Oh, so there's our laser matrix cubed. We just need to stick onto the end of it, times, where are we? Oops, nope, not that one. Options, matrix, mat, alpha, B. Enter. Right, so here we go. Let's go back to the top. All right, so this makes sense. Initially, we'll have 250 because the birth rate hasn't come into effect yet. Then we're going to have 125 in the older age period, which again makes sense. None of those animals were old enough. None of the population were old enough to have babies yet. Okay, and then we move down to L cubed. Right, so before this cycled back to the initial age period, the initial population. But now we've got 500 instead of 1,000. So all of the ones old enough to have babies haven't had enough to replenish the population. What do you think is going to happen if we put in, say, 6? We cycled through the next 3 time periods. If we go bracket matrix A to the power of 6 times matrix B, we're going to have half that again. Yep, there you go. So if the birth rate is only 4, we can probably conclude that our population is going to decrease over time, because the birth rate is not enough to sustain the population with those survival rates. All right, so that is B. Let me scroll back down. So B, if the birth rate is 4, this is not enough to sustain the population. Therefore, the population will decrease over time. And then lastly, C, if B3, our birth rate for the 3rd age range, is 10. All right, now we've had a birth rate of 8, which ended up not changing the population at all. It ended up being the identity matrix, where L cubed was the identity matrix. So every 3 time periods, the initial population returned. Okay, if the birth rate was 4, our population decreased, which makes sense. Okay, but now if our birth rate is 10, which is more than 8, 10 is more than 8, do you think the birth rate will decrease again, stay the same? Sorry, would you think the population will decrease, stay the same, or increase over time? I think I know what it's going to do. I think it's going to increase over time. So if we go back to our calculator here, we go to back to the exit, we press F3 for our matrices, enter in that one, and now let's change our birth rate to 10. Press enter, exit, exit, and let's go back up to the top now that we've changed our matrix. Press enter, and here we go. That's after 6. Go back to the top. So 250 after the first time period makes sense. 125 after the second time period makes sense again. And here we go, after the third time period, we've got 1,250, which is more than the initial population in that age range. And of course, if we go 3 more time periods, 1,562.5. So if the birth rate is 10, the population will increase over time. Done. Alrighty. Let's have a look at a second example here. So consider the following Leslie matrix and the initial population. Investigate the long-term behavior of the population. Alright, so this is very similar to our initial example, okay, except we've got a second birth rate in here. So going back to our calculator, if we go to matrices and modify this one, we want 4 here and 4 here. And that is our new Leslie matrix. Exit, exit, and we can go back up to the top and press enter. Our initial population doesn't change, but here we go. So we've got 250, makes sense. But in the second time period now we've got babies happening, which makes sense. We've got the birth rate now in the second age range. So that's happening a lot earlier, and then that's after the third time period, and then after the 6th time period. And we could also chuck in a big number. Options matrix. Matrix alpha A to the power of, let's put in, say, 100. And then we're going to multiply that by our population, our initial population. Matrix B. And there we go. Wow, so that's huge. So our population over time is just going to increase without limit. So population will increase without bound. Right, there's no limit to how big the population will go. Alright, now part B. Establish numerically what the proportion of the population in each age group stabilizes over time and determine the long-term growth rate of the population. Alright, now this matrix A to the power of 100, too big to work with. Let's make it smaller. Let's go, let's put our brackets in. Matrix A. Let's go 25. Let's go to the power of 25. P25 equals 34781.25, 7297.85, and 3062.5. So that's after 25 time periods. That's our population. And P26, okay, because we want the proportion of the population, between the time periods. So we're just going to go up. I'm just going to change that now to 26. Right, we've got 41,441.41. We'll have 8,695.31 and 3,648.93. Okay, so let's find a rate of increase, okay, but for each age group in the 26 time period. The way we're going to do that is, well, we're going to do P26 divided by P25. I'm going to do that for each of the age groups. Okay, so for the first age group, you'll have 41441.41 over 34781.25. That gives us about 1.19. Next, we're going to do, I'll do it up over here, 8695.31 divided by 7297.85. So this is the second age range now. That's going to give us, again, 1.19. And then lastly, we've got 3648.93 divided by 3062.5. Let's check this one out. And that gives us, again, 1.19. So this reveals to me that the age proportions have stabilized over the 25th time period, and the long-term growth rate of the entire female population is 1.19. So after a certain stage, the population is increasing by about 19% each time period, which makes it a lot easier to calculate in the later time periods, because you can just times that total population by 1.19 and you'll get each successive time period. So we often find that after a long enough time, the proportion of the population in each age group does not change from one time period to the next. And so if the population is consistently increasing with a certain rate each time period, so L times P star, okay, if that's equal to some growth rate, we're going to call that lambda P star, okay? So that's a real number lambda, such that this equation exists, and it's discussed more later on. Okay, and there you have it. That's all we're going to do for today. That's Leslie Matrices. I look forward to seeing you next time.